This is the progress video for the final project.
And we are the presenters, Chanhyuk, Minhak. Chanhyuk will present the first paper.
Thanks, Minak. The first paper our group will be presenting is the lottery ticket hypothesis, finding sparse trainable neural networks by Franco. It was awarded as best paper at ICLR 2019. As you can see from the word sparse, this paper focused to find sparse networks which have smaller parameters that achieve the comparable performance with the original one. That kind of technique is also a field for machine learning called network pruning. Network pruning can be done in any neural networks, including fully connected layers and convolutional neural networks and more other networks too. Usually, network pruning is performed as the following steps. First, we train the full network, and then we remove some structure of the network according to their importance. Here, structure can be anything constituting the network. It can be weights, dots, filters, and channels of the network. Also, importance can be any criterion that a user defines. It can be a magnitude, gradients, or activations, and more the user wants. Next, we fine-tune the network again. We just repeat the step 2 and 3 according to some condition predefined by the user. We can just do it once or iteratively repeat until some condition is met. There are more previous works on network pruning, but I brought the famous 2 works on network pruning. The first one, by Han at 2015, showed that pruned network have significantly lower parameters and achieve similar or higher test accuracy than the original one. As you can see in this table, VNet and AlexNet and FreeGG, they are almost compressed with a compression rate more than about 10, but they still remain the similar top 1 error rate. This, as you can see, this shows that network does not need to be that much over-parameterized in order to run some machine learning task. Also, the second paper by Lee showed that those pruning works not only work for simple networks like VNet or AlexNet, but also with deep neural networks like ResNet. As you can see over here, this table, we also test on ResNet 110, which is really a deep network, but this pruning about 15% or 40% works well without losing any performance. Then here arises some questions about network pruning. If pruned network is so efficient, why not train them pruned from the beginning, skipping the first training procedure? But unfortunately, if we just train a randomly pruned network, it does not reach the similar performance, which shows network pruning is somehow related to the initialization of the network before training. This is empirically proved by the previous 2 papers where both authors agree this. Another some controversial thing can be in network pruning is after training and pruning, we retrain the network. Then when we train the pruned network, do we just use the network weight as the trained value, like fine-tuning? Or we can reinitialize them with some other random value, right? There can be a lot of ways to deal with this problem. But again, from the previous 2 papers, it is empirically proved that using the initial random value is better than other strategies. Also, from this 2 paper, we can check that network does not have to be that over-parameterized to learn something. So, from those observations, we can define a network pruning procedure like below, which is the paper's author is presenting. First, we randomly initialize and train the network. Secondly, we remove the weights of the network according to the network's magnitude of weights. Then, we reset each remaining weights to value from step 1, which is after random initializing and train the network. and repeat step 2 and 3 iteratively again. Then we can get the graph like below. The fun part is, even the network has smaller parameters, it converges faster and achieves higher performance than the original not pruned network. As you can see in this graph, blue one is the original one, and the orange and the green one converges faster and achieves higher accuracy than the original one. Then, what is exactly making the pruned network to perform similar or better than the original network? We can compare the author's pruning technique and the original technique and find the key of success. The different thing is that the different thing is resetting each remaining weight to initialization instead of reinitializing to other random value. If you just reinitialize to other random value after pruning, it shows lower performance, as you can see at the graph below. But the caveat here is that experiment is done at a small size network with a small vision task. And also finding such a network is expensive because we iteratively find them. So what we observe here cannot be generalized to other bigger networks. We don't know yet. And we don't know if this works for other tests like NLP or other domains. But still, from these observations, authors propose a new hypothesis called the lottery ticket hypothesis. Let F be a neural network with a parameter theta randomly initialized, which is theta 0. With stochastic gradient descent, F reaches minimum validation loss L at iteration j with test accuracy A. Also, with some mask M, mask network with same theta 0, as F is trained with SGD and reaches minimum validation loss L dash at iteration j dash with test accuracy A dash. Then the lottery hypothesis predicts that there exists a pruned network for which, with smaller or equal iterations, it achieves higher or at least same accuracy, with significant amount of less parameters. Authors gives a concrete algorithm to find the winning ticket, which means satisfying the lottery hypothesis. The authors show empirically the network found with this algorithm, which is a winning ticket. Authors also gives observations that iterative pruning is better than one-shot pruning, as you can see in this graph below. And to give an empirical proof of the hypothesis, authors test on variety of networks with various options. At MNIST, we use LENet with ablation with other options such as random reinitialization or one-shot instead of iterating the pruning process. And also to prove the hypothesis to bigger networks and a bigger task, which is CIFAR10, authors test many convolutional networks like ResNet or VGG with novel options such as global pruning and changing the learning rate and also testing with the dropout. And the authors succeed in finding the winning ticket at those various cases. So to sum up, this paper demonstrates that pruning uncovers trainable subnetworks that reach test accuracy comparable to the original networks from which they derived in a comparable number of iterations. And also, it shows that pruning finds winning tickets that learn faster than the original network while reaching high test accuracy and generalizing better. And most importantly, it proposed the lottery ticket hypothesis as a new perspective on the composition of neural networks to explain these findings. Next, Minak will present the second paper.
Thank you for a nice introduction, Tanya. Okay, our second review paper is Uniform Convergence May Be Unable to Explain Generalization in Deep Learning, published in NeurIPS 2019. We will start with the background. So last year, GPT-3 model came out with 175 billion parameters, which is quite a lot, and this showed state-of-the-art performance in NLP tasks. In fact, the size of the neural networks are getting larger in the last few years, and not only for language models, but also in image classification. So in practice, bigger models are showing higher generalization performance, and this is actually counterintuitive in classical perspective. So revisiting the classical ML theory, it says that the big models should generalize poorly. This is because the standard uniform convergence bound increases as the number of parameters increase. So this fails to explain generalization of heavily overparameterized networks in practice. So you see this a classical U-shaped generalization curve, which we can easily find in ML text. And this also tells us that increasing model size will eventually fail generalization. However, in practice, as model size increases, the generalization error eventually decreases, giving this kind of double descent generalization curve. So actually, recent theoretical works are trying to explain this phenomenon, the double descent phenomenon, by searching the implicit bias of SGD. So using the implicit bias of SGD, for example, the norm-based implicit bias, they construct algorithm-dependent generalization bounds based on uniform convergence, and they try to make bound decrease as the number of parameters increase. So these learning theoretical perspectives use uniform convergence, or let's say UC, based generalization bounds, while classical generalization bounds use complexity of whole hypothesis class. Modern generalization bounds use complexity of a relevant subset of hypothesis class, considering the implicit bias of SGD. So they are trying to find a tighter, smaller complexity term at the denominator. However, these existing bounds are still either grow with number of parameters, or they are small, but they don't hold on original networks, but only for the modified networks. So motivated on this paper steps back and to study the limitations of uniform convergence-based generalization bounds. So their first finding was that they empirically observed that existing generalization bounds grow with training set size, and this is what is unexpected. And their second finding was that they proved the failure of uniform convergence-based generalization bounds in certain settings in deep learning. So we'll first see the empirical failure of UC. So the experiment setting is quite simple. They used MNIST for classification task, minimizing the cross-entropy loss with fully connected ReLU network. The stopping criteria was training until 99% of the training data. They're classified by merging at least 10. Then they measured the generalization error and existing bounds. For example, they measured the bound by Bertolet, published in 2017, and Nashabar, published in 2018. They varied the training set size. The left graph shows that the test error decreased as the training set size increased, and this is what we have expected. However, the right graph shows that the existing bounds increase as the training set size grows. So this implies that they fail to explain the dependence on the training set size. This was the empirical failure. And for the theoretical failure or the provable failure of UC, we should first review the essential concepts. So let's say S is a training set and H, S be a hypothesis picked from a hypothesis class H by the algorithm trained on S. Then the generalization error is an epsilon, which is a function of m and delta, defined by the smallest epsilon such that the probability that the difference between the test error and training error is smaller than epsilon should be greater than 1 minus delta. And the standard uniform convergence bound is defined by the smallest epsilon, such that the probability that the largest difference between the test error and the training error among all the hypotheses in the hypothesis class should be greater than 1 minus delta. So the classical generalization bound is based on this standard uniform convergence bound. And this paper introduces a new concept, and this concept is a key concept in this proof, which is the tightest uniform convergence bound. So this bound essentially considers the most refined subset of the hypothesis class H star defined by only the hypothesis picked by the algorithm across different draws of the training set. And this set ignores any hypothesis that is never picked by the algorithm, so which is the most refined hypothesis class. So using this H prime, the tightest uniform convergence bound is defined by the smallest epsilon, such that the probability that hypothesis in H star has difference between test error and training error smaller than epsilon, with probability larger than 1 minus delta. And since this is possibly most refined UC bound, proving the failure of this, the tightest UC bound, will eventually imply the failure of all possible refined UC bounds. So the proof outline is as follows. It uses the tightest UC bound, and the first step is to consider an algorithm that has zero training loss and the test error less than epsilon. Then, for each training set S, we suppose that there exists a bad dataset S prime, such that S prime is completely misclassified by the hypothesis HS, and the distribution of S prime is same to the original training set distribution. In this setting, we can prove that the tightest UC bound is greater than 1 minus epsilon because the empirical error of HS for the dataset S prime is 1, while the training error is epsilon, which means the difference is 1 minus epsilon. Therefore, the generalization error is near 0, but the tightest UC bound is near 1, and this implies the failure of tightest UC bound. So in this certain setting, in deep learning, the failure of UC bound is proven. So here is an example that fits this setting in empirical. So we will consider the binary classification task on n-dimensional hypersphere with one hidden layer ReLU network. Training minimizes the cross entropy until 99% of training data are classified correctly by a margin of at least 10. So the data at the radius of 1 are positively labeled, and the radius of 1.1 are negatively labeled. Then, using this setup, we can construct the bad dataset as following. Given the training set S, every training data point is projected on the inner hypersphere to the outer hypersphere, and vice versa. And this essentially makes the bad dataset. Because the decision boundary made by the hypothesis HS is complex in microscopic views, such that this actually makes S prime completely misclassified. So this is actually because the decision boundary learned by S is complex in microscopic viewpoint, and this makes the generalization bound larger despite of actually small generalization error. So, in summary, UC-based generalization bounds increase with the training set size, and thus this cannot explain a crucial aspect of generalization behavior. Moreover, the decision boundaries learned by deep networks can be complex, actually, so that this rendering can not actually explained by uniform convergences, because uniform convergences are so big despite of good generalization of deep neural networks. These are the references, and this is the end of our presentation. Thank you for listening.